Part 2, week 3. This is the battery. We talked about the paste and electrodes. So electrodes are the terminals that touches each other and the end of any power source. So these are the electrodes or terminals. This is what's inside a dry cell battery, like door cell energizer. This is what you will see inside. You have the paste, and there's a chemical reaction. Those two materials, when they get together, they will make electricity. If you have a lemon and you put a zinc rod in it, you will have a small battery. It's not a lot, but it can give you some power. So you can light small light with it, because this acid in the lemon will react with the zinc and produce electricity.
Also like watermelon and water.
Yeah, it has to be some kind of electrolytes inside and a reaction happening between the metal and the material. Who saw Breaking Bad? So you see when he buried the battery in the ground to recharge it? When they went to the desert to do their thing and they ran out of battery. So he buried the battery in the ground to charge it. That's actually a scientific fact, it does happen. You could do that. Bury the battery for a while to recharge it. So I know people actually who will be lost in the desert sometimes and run out of battery, they bury it for a few hours and it should charge it a little bit. Yeah,
Like
but
how
it takes a long time. It's
Like how
good.
deep do you have to bury? You have to bury like pretty deep or no?
No, like half a meter, like a foot or so.
Oh, really?
Yeah, yeah. It does happen. It doesn't give you much though. So you gotta be lucky. Okay, conductors cut through a field, cause displacement of electrons, use supply electricity to consumer. Same idea of what does, how do we do electricity through magnetism? So in magnetism, think of your car. A small little alternator, they have a huge one. At some time. Your motor is gonna be a huge boiler that turns a turbine. So think of your car, how does it generate electricity? Same thing is happening in a power plant. A turbine as big as this lab is turning a big alternator. Same thing. Or you can turn it using hydropower or wind power, it's the same thing. If you look at wind turbines, the huge room behind the turbine is basically an alternator. It's a big alternator there that is being moved and producing electricity. So we're changing mechanical power into electrical power using magnetism. Conductors and insulators, we talked about that a lot. Conductors are material that conduct electricity. They have loose electrons, so you can push things through it. Insulators, they do not conduct electricity. So they do not conduct. Examples, most metals are conductors, and most material with electrolytes are conductors. Insulators, they do not give any electrons. They're very subtle. What's an example of that? Carbon atom, very stable. Most of carbon-based material are insulators. Glass, rubber, and asbestos, they are insulators. Can we all give examples of insulators and conductors? Do you have a sense of what conducts and what doesn't? Okay. Is there any absolute conductor, insulator? No, everything will conduct. Don't assume
At the right temperature.
at the right voltage. Yeah. Important terms, we talk about voltage, volts, amperes, and ohms. This is the basis of Ohm's law. Potential difference, also voltage. Electromotive force, also voltage. Field of force, electric pressure, these are all voltage. And they're all electrical potential. So they can be used interchangeably. For us, we use volts. We're always going to use volts. Electric potential. So now we have to talk about circuit. So a circuit is basically a complete path for the electricity to go from. So now we have a dry cell, which is a battery, right? And the battery usually produces what? AC or DC? DC. We didn't get to that yet, so if you do know, it's okay. So it's direct current, which means the current will flow in the same charge the whole time. It's going to be negative the whole time. The current will go through the light bulb, get used a little bit, lose some of its potential, and comes back to the positive terminal. So if you have any cut in that circuit, It's not gonna happen. What if if I have a cut here, how come the light bulb is not on, even though it's getting power? There's no circuit. Keep that in mind. So you can get power all the way here, but there's no neutral, there's no way back, and it's not running. Remember that, because when you do troubleshooting, you're gonna go check the power from the receptacle, go all the way to the components. It has power, but it's not running. Is it broken? Am I gonna replace it? Check your neutral. Make sure that the way back is running. We had this few times in the lab. It was very, very frustrating. We checked everything. We're getting power at the equipment. We get power. Check your neutral. Check the complete circuit. Sometimes the neutral wire at the end is just loose, so you're having a complete circuit. The same thing is happening here, but this time this light bulb is running on alternating current, and we have a generator. So generators can produce either DC or AC, meaning either it can be positive or negative, or the same line will have a wave of positive and negative. We'll spend the whole chapter talking about the difference between AC and DC. For now, I just want you to know that DC and AC are different. They both make current. One of them is straight, and one of them is going back and forth. So DC, direct current. If we look at the production of current, it's going to be flat. It's going to be always negative. So 12 volts all the time. That's direct current. AC, alternating. Which means it's going to go up and down. Positive and negative, positive, negative. And it could be at any amount. 12 and 12. So it means it's going on and off many times. So all these lights are running with alternating current. So how come if it goes on and off, how come we don't notice that it's going off?
It's happening so fast.
Yeah. How fast? 60 times a second. That is the
60 hertz.
60 hertz. So 60 times a second. If you, this is kind of funny. Have you ever used the massager? Something that vibrates and put it around your head? If you do that, look at the TV and look at the light. You'll see it going on and off because your head is vibrating the same frequency. You'll see how it goes on and off. So, if we alternate the light, the frequency less than 60, you'll start seeing like the flickering. Now it's flickering, but you'll see. For us, it's okay. But it is flickering. So how do equipment run with that? They are designed to run with this on and off. It's going on and off all the time, 60 times per second. And again, you can see it if you like go really fast, and if you lower the frequency, you start seeing the flickering, noticing it. Sometimes during thunderstorms, if you miss up the frequency, you start seeing the flickering a little bit. That means it's going on and off. But they are designed to take that on and off a lot. Okay. Questions about AC and DC, just from this point of view. DC is constant. What current do you have in your car, AC or DC?
When?
Huh?
Oh,
No, inside the car, the whole car. DC. The alternator have AC, but it changes right away to DC. So it goes to battery as a DC. That's why they have a voltage regulator inside the alternator. And sometimes when it goes out, you hit the gas and you can see that the ampage was really high up. It doesn't happen now with new cars, but it used to do that. You have a car from the 80s, and your alternator is going bad, you hit the gas, you see everything is brighter, the headlight and stuff, and when it goes down with it. Question?
What about a hybrid car?
Okay, what?
What about a hybrid car?
That's different. Probably it's all have AC, both AC and DC, but I'll say it's mostly DC because it has a lot of batteries. And if you generate power using AC, you have to convert it to DC. They're both effective, they both do the same job, but the advantage of AC is what? It goes further. It's good for transmission.
So with the solar power, how is that energy efficient? And where are those batteries at? Where are they at? Because I mean, if to transfer that DC power, there would be a voltage drop.
They change it to AC, they have an inverter. They change it, they transform it, they put it back. The reason is, he was saying that photovoltaic panels uses and produce DC current. So usually in your house, if you have panels, they have an inverter. They have a battery and have an inverter. The battery will take the DC, but there's an inverter that goes to your house from that battery. It's change DC to AC. Okay? If you, again, put your multimeter on DC, I'll show you how this happens. Put it in DC and you put it onto the receptacle, what are you gonna see? A very quick change between minus 120, plus 120. It's gonna flicker, minus plus 1, 60 times. Because it's trying to read DC, but it's getting AC. Okay, current flow, electron flow in electric circuit obtained by a bolt find inside electricity or electron flow from a generator. Okay, that's very, we know that. Again, direct current flow in one direction, that's the one direction. Alternating current, it goes back and forth. And amps are the unit of measure of current. So, put the units here. Volts. What is current? Amps or amperes. Again, ampere is another good guy who invented something. Resistance is ohms. You gotta get something. Probably you gotta assume that Watt is named after James Watt, who invented the steam train, steam engine. So, well deserved. Okay, so opposition, that's the resistance. That what goes against the amps. So in our example here, that's like the taps, the faucet, the shower head, that's also going to be your resistance to the flow. For us in a house, your AC is a resistance. All the loads, your oven is a resistance. They actually eating the energy out of the flow. Pressure, so let's see how they compare it to the pressure. When we see VAC, what does that mean? Voltage AC. And this is the electrical heater that's taking the flow and the current over here. Okay. Electric power and energy. I think I'll stop here and finish this on Wednesday.